like I mentioned, I'm going to be picky on those, like right or wrong. I think there was one exception I made where somebody was doing the tangent alpha plus beta, and they did tangent alpha plus tangent beta over 1 minus tangent alpha beta instead of tangent. And I think on that one, I counted off half or something like that. But on the other ones, it's just right or wrong. And the point of that is you're going to be applying these identities. You'll start seeing the application today. And if you start out with a wrong foundation, it's like building your house in sand. You're not going to be able to withstand that problem at all if you start out poorly. So I want you to start out strong with a strong identity, and then you have a fighting shot of actually getting to where you need to be. And you can do it. I mean, I was looking at these. We had a number of people in here who got beaten up on that quiz, but at least half the people had perfect scores. And then there were a number of other ones who had 19s and 18s, which are all A's when you count out of 20. Out of all 47 of you guys, I want to say close to 30 had perfect scores. So they're attainable. It just takes some time. I mean, it's not like some math where you guys are just really smart. You can just pay attention. Memorization just comes at a cost. Unless you have a photographic memory, you're going to have to spend a little time on it. So if you got beaten up, remember I dropped your lowest. And I will do that, although ideally for those of you who got 20s, probably don't want to drop a low. Have 20 out of 20 on all of them, and you got a nice padded 80 out of 80. But I do drop the lowest one, so if you got beaten up, seriously, find a way to do well on the next three. Yeah.
Will you record?
It's recorded. It should be. Yep.
Mine's in power school wrong.
You what?
Mine's in power school wrong. I guess it says the wrong range in power school.
What's it say? Well, hold on. Like in your advantage?
Yeah.
Like way in your advantage?
Oh yeah.
Yeah. I don't know how that happened. Huh. Well, my policy is kind of a Merry Christmas policy that once you're sitting on it, I appreciate your honesty though. Anyway, so please figure that out. And yeah, that's right. Honest guy. I like it. Figure out those identities. Make some adjustments to how you're studying because we're adding more to it, right? We're adding another batch, and then we're going to add another batch. So the double angles will come in after today, and then the half angles will come in on that third one, and then the last one's all of them. Okay? So for today, I want to actually shift gears a little bit unless you have a question about some of those identities. Anybody? Got a question about something on the homework? Nobody? If you're skipping those, and listen, I know the temptation. Man, he puts the answers on Schoology. What a sucker. It's not me that's the sucker. Like, I know my identities. I know I did really well in classes beyond this class. You're only hurting yourself. I know it sounds like a parent, but like, you're like, whatever. But you are. It'll come back to haunt you eventually. Maybe it shuts a door for you being successful in a class that keeps you from being an engineer or whatever. That stuff kind of, that's an extreme, but I'm saying those little steps, they do make a difference. So hop on it and totally you can get it, but you might want to spend a little bit of time over spring break at some point because that next quiz is going to be on that Monday. Yeah. Can you give me the page? Next book, go, Mika. Oh, never mind. Page number 37 on page what? 639. Say it again, 30.
37.
37. So 37 said to prove. Tell you what. 37 said to prove, and this is on page 640. So it was cosine to the fourth x minus sine to the fourth x equals cosine squared minus sine squared. So a number of ways you can go about this, but again, I'm proving. So when you're proving, what happens? You are
setting the two sides.
You are-
It's the same thing.
you are trying to make one side equal to the other, and I don't have to make this equal that. I don't have to make this equal that particular side. I could work on this a little bit, maybe factor it or something, work on this a little bit. But what I can't do is treat it like an equation. I can't go in here and say, oh, I'm going to divide both sides by cosine to the fourth, or I cannot do that, right? It's not about that. This is basically saying, is the left side equal to the right side? And if it is, make it happen. Okay? Just make it happen. So right here, I'm going to look at this and I'm thinking about my rules. It's already, and remember, I'm using my simplify rules on one side or maybe on the other side, but never simultaneously on both, because that's algebra. We're not doing that. So it's already in the numerator. It's already sines and cosines. I don't see any Pythagorean identities at all, but one of the rules is what? One of the rules is factor, right? And I see a difference of two squares. Now, both of these are difference of two squares, but I'm just going to look at this one on the left because it's a little bit more complicated than one on the right. And if I factor that, as this is something squared, so how would a cosine to the fourth break up? Cosine squared, and sine to the fourth, sine squared, and plus minus. And then, oh my gosh, what do I see here? That's equal to 1. And 1 times this is cosine squared x minus sine squared x. And at this point, I have made the left and the right match. I'm finished. But again, if I don't know those 8 steps that I gave you as far as suggestions when you get stuck, and all I'm doing is the last one, sitting and staring at it, I'm not going to get anywhere on these things. You got to try something. You've heard me say the expression, a rat in a maze. Have you? Little probably. Okay, when I say act like a rat in the maze, when you put a rat into a maze, it doesn't just go, and just roll over dead. I mean, it starts sniffing around, right? It starts figuring its way around. And at some point, it navigates it. It's got a good memory, very smart animal, and it'll find its way out of that maze eventually. But it doesn't quit. It doesn't just sit there and hope for, a helicopter to come in and airlift it out. So you've got to kind of look at these problems like that. I'm glad you all mentioned this. I brought this up. Don't expect to know where you're going. A lot of you have been the smartest kid in the class since you're in 4th grade math. It's been a joke. You haven't really been challenged until maybe Tyree, maybe Helmer's, maybe this year. And you're used to looking at a problem and going, oh yeah, or oh yeah. It didn't mean you could solve it, but you had an idea. You're used to that. You're not going to always feel like that on identities. You're not. You literally got to go, well, let me just try something. And usually when you try something, it's like, oh yeah, and that simplifies. Oh yeah, and now I have the same thing. I mean, it's a step process that at some point the clouds are going to part and you're going to see where you're going, but you're not always going to see where you're going initially. I mean, I recognize all these problems after 29 years of looking at them, but you're not. And when I do see a new problem, my brain is just scanning through my ideas. I mean, my rules. Like when I look at it, I'm not just going, I'm going, could I do this? Could I do this? And I'm kind of manipulating it in my head until I got an idea. And if I can't see it, I just try something. So don't be afraid to just try something on these problems. And then don't erase your stuff. If you don't get anywhere, stop. I might look at it and go, oh man, they did so much right. They just didn't see that last part. And you might just get dotted. Or you might get slashed on a 3-point problem or 4-point problem and miss a couple points. But show me what you're doing because there's a lot of value in it. Oh, and one last thing. I also realize that y'all are smart. And I see this all the time. There's actually a cartoon I have up here. I don't know if anybody's looked at this. I had this friend in college. I don't know if he's really a friend. He was in my study group. But his name was George. And George was a genius. And we were in a proof class. And I remember asking George, okay, I'm looking at your proof. And it makes perfectly good sense to me. But how did you know to do that? And he'd go, dude, I don't know. I just know. I'm like, you got to do better than that. He goes, I'm not kidding. It just made sense to me. I'm like, he would pull these things out of thin air. He was on another level. He was working. I was working on my master's in education, so I was doing a couple graduate math classes. He was working on his doctorate in mathematics. I mean, brilliant guy. But he was like, I don't know, I just know. And that whole thing right here, if you're looking up here, he's writing this formula, and then he goes, then a miracle occurs, and then he finishes it off. Well, I see people do that with these proofs. They know that sooner or later, the left side and the right side are going to equal, right? And some of you are smiling already at me. But like, literally, I'll see them do this. Well, this is the simple side over here. So I'm just going to write this down. And then I'm going to write a bunch of crap in here, and maybe he won't notice. I'm not kidding. I'll notice. I read every single one, and I recognize after the years of these, the different strategies. Now, you might get lucky, but I'll say this. If I can tell it's completely junk and you did this, I count off a lot more severely than I would if I did. So don't do that. I can sniff out and miracles as they're happening. All right. But yes, most of them do end up looking the same, but you got to get there. So if you can't get there, don't worry about that. I may give you a ton of credit for what you did right. But if you do a bunch of stuff right and then a miracle occurs and you're trying to pull wool over my eyes, I tend to be a little bit harsher with my grading because I feel like you're trying to pull one over on me. Anyway. Anybody else? Okay, so here's what we're doing today. The sum and difference. Oh, yes.
I have this thing that
Go ahead. Make it quick.
number 45.
That is not quick. Were you here yesterday? Oh, wait.
Well, I can look at the key. I usually understand it whenever.
I just did it. Or some. Oh, I don't throw it away.
I'll look at the key.
Okay. I can do it later when we get back if you want. Or after school if you want to zip by here. It's a long one.
Okay. I think I can probably.
All right, so look at these sum and difference identities. We had them on your test. Well, not look at them, but we had them on your test yesterday, the last 3 ones, right? And people are like, why would I ever use these? Here's why you would use them. Okay, and I'm giving you some practice problems, but even before we look at these, let me just show you. There are going to be times, and I might have already mentioned this, but there are going to be times when somebody asks you to do something like the sine of 75 degrees or the cosine of 15 degrees. And you look at it and you're like, and you don't have a calculator. Right? And you look at it and you go, well, that's not a unit circle value, so I guess I can't do it. However, there are unit circle values that either add or subtract to give me both of those. Now, this method won't work for every angle, obviously, but it'll work for a lot of them, or some of them, not a lot of them, some of them. So in this case, I look at 75, and a lot of things add or subtract to give me 75. But in terms of the unit circle angles, what unit circle angles, and there's a bunch of them, what would add or subtract to give me 75? So I'm hearing 30 plus 45, right? I could have done 120 minus 45, right? I mean, there's a lot of options. Don't use 60 and 15. 60 and 15 do give me 75, but I still don't know what to do with the 15, do I? So if you can find 2 angles that either add or subtract to give me that, what if I just put myself in it? A what? A sine of an alpha plus a beta, right? Now, a sine of an alpha plus a beta, what is my identity? Sine of the first one, cosine of the second, and then keep the SIGN, right? And then cosine of the first one, sine of the second. Now, for those of you who are like, why can't you just distribute it? Literally, we proved these identities 2 days ago, right? I would love to be able to distribute it. It's just not right. I mean, think about it. What is sine of 60? What is that? Unit circle. Square root of 3 over 2, right? Because 60 degrees, you're going over a little, up a lot. So that's root 3 over 2. So if I could break that into 30 plus 30, and all I had to do was distribute, if that was true, what would I end up with? What's sine of 30? Is a half plus a half equal to square root of 3 over 2? Then clearly this doesn't work. Right? It just doesn't work. It'd be great if it did, because we could just go, I don't have to do any of this. I mean, it's just common sense like this. And you're like, if you're like looking at it going, why doesn't it work? That's the distributive property. The distributive property works with numbers, not with functions. You can't distribute a function in. This is a function, right? So it doesn't work. So, but this does work. And now I can simplify it because now I know those unit circle values. So I can come in here and go, well, sine of a half is 30. Cosine of 45 is root 2 over 2. Cosine of 30 is root 3 over 2. Sine of 45 is root 2 over 2. I can multiply this and get root 2 over 4. I can multiply that and get root 6 over 4. And then those do not add, right? You remember that? So all of that would just be over 4. And you are welcome to skip that little middle step and jump to there. But don't forget it ends up being 4 on the bottom. Are y'all seeing that? So that's the application of these. And then back to the other one. If I asked you for cosine of 15, can you think of two angles that add or subtract to give me 15? Say 45 and 30. And there are other ones, right? I mean, there are lots of them out there that you could do. But yeah, I would go with 45 and 30. Right? So how do I simplify cosine of alpha minus beta? Cosine of the first, cosine of the second, and then that negative becomes a plus, and then sine of the first, sine of the second. And then once again, root 2 over 2 times root 3 over 2 plus root 2 over 2 times the 1/2. And you start getting used to seeing these root 6s and root 2s. You see a lot of them when you're dealing with these alpha plus betas. Except some of them are both positive, some of them are, well, actually both of these are both positive. Oh, why is that? Because these are co-functions, right? Sine of one angle is the cosine of 90 minus that angle. So that's why you ended up with the same value. All right, but that's what goes on here. Now, if I go back up to the beginning of this worksheet and I'm looking on page 49, if you want to jump around. I gave you one kind of broken up to start with. I don't want to go 120 minus 45, or that sends me right back to what? 75, and I'm stuck. So I've already got it broken up for you, but don't distribute it in. If I distribute that in, it looks like this, doesn't it? And if I simplify that on the right, cosine of 120 is left a little. If I go cosine at 120, I'm going left a little bit. And cosine of 45 is same each way. I get -1 minus root 2 over 2. That's what this is. But clearly, I get something completely different when I apply my alpha minus turns to plus, alpha minus beta formula for this, don't I? Also, a lot of you are forgetting to put the little degree sign. I'm not counting off, and I don't know that I ever will, but this year. But at some point, you need to put those, because if you don't put a degree, it's assumed to be a radian. Okay, so right here, cosine of 120, that's a -1/2 times the square root of 2 over 2. Sine of 120 is the square root of 3 over 2 times the root 2 over 2. And then once again, you can see I get a lot of these root 6s and root 2 things. But this one actually changed sign on the root 2. Are you tracking with me? And that's the alpha plus beta identity. And sometimes it'll start looking a little ugly. I've already done this number 3, this sine of 45, so I'm going to skip it. But look at number 4. Number 4, do you know how to do any radian values that have 12s on the bottom? I don't. All of ours have 2, 3, 4, 6, right? Now, you'll learn another method Monday, maybe, that's called, Tuesday, which will help you do a half angle identity with this. And that's so much better with tangent than what I'm about to show you. There's a ton of algebra that's going to be required to simplify this. But I would argue that this right here is a little uglier than 75 or 15, isn't it? You know, but it is half. You think about that 12. 12 is basically me taking think about this for a second. If I had a 13 pi over 6, that would be something on my unit circle, wouldn't it? Well, it looks like I took half of this. Okay? And if you think about the angles that have 6s on them, there's stuff like what? The 6s in the denominator? 30s and 150s, right? 210s, right? So if you think about those, if I took half of those angles, it would be like 15s, and half of 120 is a 60, half of 210 is a 105. All of those angles can be simplified with alpha and betas. Now, you may not know that right now, and that's neither here nor there. So here's what I'm going to do. The radian's bothering me a little bit right now until I learn half angles. So what I'm going to do is just change it to a degree. How do I change a radian measure to a degree measure? Have y'all learned this? How do I change inches to feet or feet to inches? Stoichiometry. So stoichiometry is a process, if you don't know this, of putting two different kinds of units over each other that represent the same thing. Like 12 inches over 1 foot. That represents the same thing. And even though 12 over 1 is not 1, it does kind of act like the number 1. So stoichiometry allows you to multiply by something like that without changing the actual meaning of what it means. It just has different units, right? It's like multiplying a fraction by 6 over 6. It looks different, but it still means the same thing. So if I have 13 pi over 12, and I don't see a degree sign, that's a radian value, right? So if I want to change it to degrees, I need to multiply something degrees over something radians that mean the same thing. What's the simplest radian and degree value that you have on the unit circle? I like 180 and pi. 180 and pi are great because they're not fractions, but they're in the same place, right? So I could multiply by 180 degrees over pi radians, and I don't have to put the radian there. And look, the pi's cancel. The 12 goes into that 15 times, and when I multiply what's left, I get what, 195? So that means that 13 pi over 12 is 195 degrees. And now I see it. What two unit circle angles could you replace 195 with? And there are a lot of them. Do what? So you could go to,
180, 15.
I like, well, 180 and 15. 15 is not going to work because I don't know what to do with 15. You said what now? 240 minus a 45? That works. I like a 150 plus a 45. That works. There's all kinds of them that'll work. I'm going to go with hers because she mentioned that first. But that can be replaced with a 240 minus a 45. And I've got an alpha minus beta identity. Now, you're going to see the algebra here is atrocious. I'm going to show you a half angle identity on Tuesday that makes this about a 3-step process. This is going to be about a 1-step process to put it in the identity and about a 7-step process to simplify it. What better days lie ahead? But anyway, what's my formula for this? It's so ugly, I'm going to come over here. What is it? My rule is tangent of the first minus tangent of the second over what? 1 plus tangent of the first times tangent of the second. So getting it into the identity was easy. Changing these with the unit circle is also kind of easy. What is the tangent at 240? By the way, you would be wise to memorize this about tangent. If it's a unit circle value, if it is, all of the tangent values that are steep, the ones that have 3 on the bottom like the radians, but the ones that are closest to the y-axis, they're all root 3, with the exception of the sine. But we already know about sines, right? Tangent's positive there, negative there. All of the reference angles that are smaller, basically the angles like 30 and 150 and 210, the ones that are closer to the x-axis, those are all root 3 over 3. I have this memorized, and it just makes it, I don't have to put y's over x's anymore, except for where they're positive or negative. All the ones in the middle are what? 1, because the x and y's are the same. So all of these are 1s, again, except for where they're negative. And the only other ones I haven't mentioned are what? The quadrantals? Well, if it's y over x, when y is 0, they're 0. But when x is 0, they're undefined. Now, again, a lot of people don't memorize that the first time they see it. But when I look at this and I see 240, I'm like, oh, 240. That's one of the steeper ones. That's a root 3. And it makes it easy for me. No. Come on, man. Did this yesterday. Totally frozen. Good times.
Is your computer still set? Oh, that's why.
Now nothing. Come back. Come on, man. Get this board. Actually, I really don't hate it, but that's just so annoying. All right. If you see the little thing pop up, let me know. So, such a waste of time. Yes. What page was that? 49. Okay. Okay, I'm going to jump to where I was right here. I'm going to have to skip the rest of this. Come on. Yes. Okay, so I was at tangent of 240, right? Which is root 3. And then I had minus the tangent of the 45, which we know is 1. And then on the bottom, I go 1 plus, and I put those same two things together, but this time I'm multiplying by them. So after I do that, I'm left with root 3 minus 1 over 1 plus root 3. And what are you going to have? Actually, this one was better than normal. If I have a root 3 over here and a root 3 over 3 here, then I've got to get rid of fractions first, multiply by reciprocals, cancel stuff out, and then get to here where I rationalize the denominator. But I got to rationalize this, don't I? How do I rationalize it? Multiply by the conjugate on the top and the bottom. So here, and again, you're going to do the half angle on Tuesday, and you're going to see it's a lot easier. So when I FOIL this out, these are not conjugates on the top necessarily. So I end up with root 3 minus a root 9, which is a regular 3, minus a 1 plus a root 3. But on the bottom, I get 1, negative root 3, positive root 3, minus 3. So on the top, I end up with what? 2 root 3 minus 4. And on the bottom, I end up with a negative 2. And can I simplify that? So that would give me a negative root 3 when I put that together, plus a 2. And it can be worse than that. On a test, I would give you a problem like this, but you would have the option then of doing the half angle formula. The half angle formula, you plug it in there, change it to root 2s and whatever junk, and then it's like one step and you're done. So it works much easier than this alpha plus beta tangent, which always gives you a binomial that you have to rationalize. There's a half angle tangent that gives you a monomial, really easy to clean up. All right, let me show you some of the trickier ones, though. Come down here. And this is a great little test question. I don't know that I have ever not had this on a test. A wise person would go, oh, okay. Leave a little trail of breadcrumbs for your success. All right, so the question is, what is the sign of an angle that I don't know minus an angle that I don't know? Now, convention would suggest that I need to find what those two angles are and subtract them. And if I had a calculator, I would just do that, right? If I had a calculator, I would do inverse sine, find that angle, inverse cosine, find that angle, make sure that the angle that I found is in the right quadrant. If it's not, use the reference angle to find the one in the right quadrant. By the way, that's what this is saying right here. Talk a little bit more about that. But we don't have a calculator. So I'm never going to find this angle. If I go inverse sine of 3/5, do you know anything about an angle of a triangle that's a 3, 4, 5? Nope. I don't. It's not a special triangle. Do I know anything about a triangle that's a 1, 4, root 15? No. So I'm not going to find the angle. So the question is, can I at least find something out about this theta? Like maybe the triangle that goes with it. Because check this out. Now that I have an alpha minus beta identity, even though I'm never going to find that, because I can't find theta and beta, can I do this? The sine of the theta times the cosine of the beta minus the cosine of the theta times the sine of the beta. This keeps me from having to find the angle. All I need to know is what? Not just, I don't have to know the angle. I just need to know the two sides of the triangle that go with that angle. And then I can just use the ratios. Does that make sense? Because the sine of an angle is a ratio. So if I can just figure out those two sides, I'm home free. But I can figure that out. Look at this theta information. This is telling me that if I knew the theta, if I knew it, the opposite and hypotenuse side is 3/5, right? But what does this tell me? The angle is between 90 and what? And 270? So it's in the second or third quadrant. So let's think for a second. This is my theta information. If I know that the angle is between 90 and 270, right? If I knew that, I could draw a picture of a triangle there or a triangle there. And I could think about that as my theta, even though it's really measured in standard position. But wait, sine is a positive 3/5. Could that be it? No, because if I think about this angle, opposite over hypotenuse, that would have had to be a negative. Are you with me? So that can't work. So that means it must be right there, where that's the opposite over hypotenuse. Well, if that's the opposite in hypotenuse, can I find the missing side? It's 4, right? 3, 4, 5 triangle. And now I can answer any question I need to about theta. What is the sine of that theta? Well, I already knew that, actually. They told me 3/5. Don't replace the theta with 3/5, by the way. You're replacing the whole trig function because the sine of the theta is the ratio. Now, what is the cosine of that angle? I needed that too. Actually, that 4 is wrong. What should it be? -4 because I'm going left. So the cosine would be -4/5. I can bring that in there. But I still need stuff about beta. Okay, well, let's write down my beta information. What do I know about beta? It's between 0 and 180. So beta is going to occur here, right? Now, I could draw two triangles there, one there and one there. But what do I know about cosine? It's negative. Cosine's positive in the first and the second. It's negative in the third and the fourth. So where must it be? Where? In the second. I'm sorry, I said third and fourth. Its cosine's negative in the second and third. It's positive in the first and the fourth, right? So since I know cosine's negative, it must be right here. It's not going to be that. Well, okay, what do I know about it? Cosine is adjacent over hypotenuse. So that must mean that I'm going left 1, hypotenuse 4. And if I needed to, it's not a special triangle, but can I find that missing side using the Pythagorean theorem? So I set it up and I solve for this y value, whatever, so I get a root 15. Now that I know that angle, right, that angle beta, this is the beta stuff, can I find the cosine of the beta? Well, actually, I already knew that. It was given to me. But can I find the sine of the beta? Yeah, root 15 over 4. So what did I end up with?
Would it be root 15 or would it be root 7? Because aren't you squaring negatives?
4 squared equals -1 squared plus the y squared. You with me?
I was thinking
Yeah. Yeah, no, keep asking questions. So right here, I get a -3 over a 20 Right here, the two negatives cancel, and I get a positive 4 root 15 over a 20. And don't cancel the 4 and the 20, or then you don't have a common denominator. So in the end, you get a negative 3 plus a 4 root 15, all of that over a 20. And I normally skip this right here. I don't write it. I just kind of go negative root 3, positive 4 root 15, all over 20. And that is a very common question. Let's try another one. What if I gave you, everybody have this that wants it? Okay, what if I gave you this? Use the sum and difference identities. Okay, so this is a different way. This time I'm giving you part of the identity, asking you what to do with it. So do you recognize this identity right here? Now, first of all, can I simplify it right now? Because if that was like a 210 and a 30 and a 210 and a 30, I could just simplify it using unit circle values. But I can't really do anything with the 230, can I? Right? So at this point, I go, well, can I clean that up a little bit? Does that remind you of any identity? The sign of the what? Alpha minus. On the sine, it doesn't change signs. On the cosine, it does. So this to me looks like a sine of a 230 minus 30 function, which is sine of a what? 200. Now, can you think of any two unit circle values that you could use to add or subtract to get me 200? I'll save you the trouble. I can't. You're not going to, you can't. I mean, if it was 195, you could, if it was something, but not this. So if you can't, you're finished. Can't go any further without a calculator on that. What about number 7? Does that look familiar? That looks like a tangent of what? An alpha 140 minus a beta 80. Now, what is 140 minus 80? Oh, wait, I got a unit circle value all of a sudden. What's the tangent of the steep ones? Root 3s, and it's in the first quadrant, so it must be positive. Done. What about this? You recognize cosine, cosine plus sine, sine. Seems like a cosine of a alpha. Change that beta. And what does that equal to? Oh, wait, I know how to do cosine of 210. At 210, I'm going what? Left a lot and then down low. So negative root 3 over 2. Are you seeing this? But it's a matter of knowing your identities. If you're looking at this and going, if you don't know your identities, you're not going to get anywhere with these, which is why it's so important that you know them perfectly. Or if you consider this a plus, you're going to end up with cosine of 250, and you can't simplify that. All right, so you miss it by not knowing the identity, and then you can't simplify it to that, so you miss both parts. So you really got to know those identities well. Let's go a little further. We got a little time. All right, what about this one? Does this look familiar? I didn't use thetas and betas. I used x's and y's. Don't let these x's and y's be confused with side x or side y. They're just variables. I'm just trying to expose you to different stuff. What is this saying right here? That the tangent of that angle has this ratio, and that the triangle associated with that angle shows up where? Between 90 and 270. So I'm going to go ahead and say, all right, let me get a little vision for what angle X looks like. This is angle X. We know it's showing up somewhere between 90 and 270. And the tangent, that could be in either quadrant, right? But wait, where is tangent negative? Second and fourth. So it must be in the second. So I draw a picture of my triangle there, and I label that angle X. And if the tangent of that X is negative 4 over 9, that would have meant the opposite is a 4, the adjacent is a 9, and the minus would have to go with the adjacent, wouldn't it? Because that's the left. With those two values, can you figure out the hypotenuse? So you square that, 81, you square that, 16, you get 97, square root of 97. That does not feel right to me. Yeah? Does it feel wrong to anybody else? It doesn't feel right. I don't know why. I remember most of these problems. I don't remember that one. All right, what do you know about angle Y over here? Y is between what? it's between 180 and 360. But I also know that when I cosine y, I get 2/3. Well, cosine's positive in the first and the second, so it must be what? I'm sorry. Cosine, yes, you are right. Cosine is positive in the first and the fourth. So this must be where? In the fourth, because those can't exist in the third. One of them would be negative there. So I draw my picture in the fourth, right? This would be my angle y right there. But I'm curious. I mean, I need to know the adjacent is 2 and the hypotenuse is 3. And with the little Pythagorean theorem, what do I find out? Root 5, but I'm going down, so negative root 5. There are a lot of lazy people on this test that they do this. They go, oh, tangent. And they just go 4, 9. I don't know where the negative goes. I'll just pick. And they'll right over here and they'll go, that's x. And they'll go, all right, here's y. And they'll write y and they'll go, oh, yeah, 2, 3. All right, that's a root 5. But because they didn't draw it in the right spot, they can't identify where the negative goes. They're not paying attention to this. This is a clue as to where you would draw your triangle, and that triangle is a clue as to which sides end up being positive or negative. So if you think about it in your head, you could still be okay, but I'm just saying drawing a better picture is a great way to save. I won't erase. Save yourself. All right, so what do I need to do here now that I've got some information? Yeah, are you going to be able to figure out what x and y are from this? No. So why do I want to try to add x and y? I'll never find x and y. So I need to get rid of angle x plus y. I don't know what the sum is. So what I'm going to do is rewrite that as what? Cosine x cosine y minus sine x sine y, and then I don't have to look at that anymore. All I have to do now is find the cosine of that x. Well, that's easy. Negative 9 over a root 97. And the cosine of that y, well, they told me that 2/3. And then the sine of that x, 4 over a root 97. And then the sine of that y, negative root 5 over 3. And when I'm cleaning this up, I get negative 18, positive 4 root 5, all over 3 root 97. And before you're done, you probably want to what? Rationalize. So I'm not going to do that on this. And no, you're probably not going to get something kind of ugly like this. But in this case, you would just distribute that in, clean it up a little bit. I probably didn't think through this problem enough. I try not to make the math just atrocious. I got 3 minutes. All right, what about this last little thing? Oh yeah, this is a little ugly, but let's just look at it for the time we have left. This says find all the solutions to the equation. Well, all we've done is stuff like sine of angle equals blah, right? We've done inverse sines or used the unit circle. Anybody got a desperate idea what they might do? Yeah, 0 to 2 pi means 0 to 360, right? So you only have the angles that would be in one rotation of the unit circle, but they are asking you to use radians. That's what it means, use radians. So anybody got an idea since we're on the alpha plus beta section? What about sine of x cosine of pi over 3? I'm just doing this part. Plus cosine of x sine of pi over 3. Isn't that all of that this? Plus, can't I take this now and put it over here and go sine of x cosine of pi over 3 minus cosine of x sine of pi over 3? Couldn't I do that? And that would give me, that's all this part right here. Now, what happens? I see that these two parts are what? Opposites, they cancel. And these two parts are what? The same, so I must have 2 of them. And does cosine of pi over 3 simplify? What's cosine of pi over 3? Right a little bit. So I get a 2 times the sine of x times a 1/2 equals 1. Ah, 2 and the 1/2 cancel, and you're down to this. Tell me, where on the unit circle, what angle could you sine and get 1? Except we're in radians, right? Pi over 2. So x is pi over 2. And that's the only one. -1 would be 3 pi over 2. You can keep it. Hey, do the best you can on your homework. Remember to study for all the same identities that you knew. A lot of you did great. Some of you need a little bit of work. That's okay. And remember to study for the new double angles. They're going to add those on as well.
Just these double angles and these all.
And then everything prior. So everything we had and that. Is anybody about to check out? Hello? Yeah, sure.
You get a comment.
Like actual tests.
It's gotta be.
All right, y'all be safe. Make good decisions. Good luck if you're trying out for something. Anybody trying out for Star Spangled Girl? Are you the only one here?
I missed it.
Caroline?
You trying out recently?
The mascot?
I missed it.
Yeah, why is it like, if there's a diamond doll, why is it like a spangled dude? You know? Where they have to go and buy you food and treats and stuff? Yeah, bring the assignment sheet.
Hey, I got it.
No, half will be the Tuesday.
I got 45. I just thought I was doing something wrong, but when you were like, oh, it's a long problem, I was like, maybe it's just pumpkin, and I got it.
Good, good.
I was on the right
It
track.
is a little tedious, though.
Yeah, I was just like, this cannot possibly be the way to do it.
Yeah. Good, good. See you guys. Y'all have a good one.
I'm just gonna-
Mr. Hurry, instead of having a lesson, we should like.
Instead of what?
Instead of having a lesson today, we should like not have a lesson.
That's how they started. They came in here talking that way. What's wrong with you guys? You signed up for this class. You want to learn more.
I do
Oh,
want
yes.
to learn more.
You want to be challenged.
Oh, I do. That's what we want. Just not today.
Well, I feel you there. But since we're here,
If I just disappeared right now, would you count me absent?
I look up when the bell rings. Nice.
I know.
Old school. I did not make those. See, everybody thought I did. I was like, I didn't do anything that's so vain. I'm not gonna do it.
Mr. Helmers told me it was just like a student.
It was Will Simmons. Yeah, he'd been talking about it for like 2 years doing it. I'm like, I used to do t-shirts every year to raise money for like Pi Day parties or whatever. And I was like, I'm not doing that. He was like, can I do it? I was like, I can't stop you from doing it. He did it on the side. And the first batch he made, he made like $5 a shirt. And then he realized I can make a fortune. So he did another batch and he's selling for like 30 a shirt. He sold like 400 of them. I mean, I bet he cleared $1,500.
I think I need to do that.
Yeah, there's a risk. I mean, but yeah, he killed it. Hey, you here today? Faithful ones.
Wait, so does the clock go off tomorrow for spring break?
Should go off tomorrow at 3:10.
I guess it will. It was supposed to be today, and then I forgot about the, this is slow on daylight savings. Like back in 98, when this was made, daylight savings didn't happen until April. So it has it built in, but now it's early. So when I set the date and the time, I picked the wrong date clearly. But I didn't factor in for it's not knowing about the new daylight savings. Whatever. Kenneth here today?
Yes. He was earlier.
He wasn't last year.
Jackson Barr's here today?
Yes.
Yes.
Jackson Kinder's not. Yeah, he left it.
You're here still?
Wow, that's like
What about Kayla? Kayla's here.
Wait, is that yours?
I'm trying to leave. Turn your your mom chickens out.
Oh, she's not here?
Turn their
I know what's
your mom
happening.
check me out. Did she actually?
Who else needs to check out?
Want to go see your mom check me out? I'm not.
Like,
I mean,
if you want,
you up here?
if you want to go, Nate.
Yeah.
We can get an early head start.
Ben still here?
We should do 8 hours tomorrow.
Oh, there you are.
Before 7 a.m. Or leaving at like 8 a.m. Yeah.
Wait, what?
What? Yeah.
What?
Also leaving the night.
Where are you going?
We're both.
I'm feeling good.
Y'all are going to university stop here. No.
You're just going to university. Oh,
Spring break and we
Elliot.
No, are y'all going separately though, or together?
both. We're not staying together, but we're going together.
Oh, yeah.
But then we're staying together.
At the beach.
Yeah.
And then they're not staying.
That just doesn't make sense.
Yeah, that doesn't all make sense.
I'm the mathematician.
You can't stay in the same
It's not
hotel.
Yes.
Why?
Because there's two families.
Okay.
There's only like 6 beds.
Hey, man, it's so thin.
I know, it's kind of nice.
Whenever I
It's
see
cool. You know, in the old days,
Whenever I see
they would max this class out at 17 people. Like, I remember once there were 18 people in my math team algebra 2 class. No, I guess it was not. There were 19, and Lada Johnson was in charge of that at the time. And he was like, that's a lot of people. We better split that. And they made it 2 classes with 19 because that was way too many. And then we got into some financial difficulties, some bad accounting, and they jumped class sizes up to like 100. But yeah, they used to be smaller, and it was nice, a little more intimate, you know. Anyway, anybody have any questions? And I'm saying that there usually are some, but are there any questions on that homework that you ran into an identity? If you're skipping those or just copying the work in the key or whatever, it's a bad idea. Again, you're going to need to probably put in a little bit more than you have in the past if you want to do well on this test. So does anybody have a problem that they were struggling with, they want to see? I'll go through 1 or 2. Yeah.
25. Or like just that section.
Right, the first one in terms of the second,
Yeah.
that thing? Okay, so I don't see you seeing a lot of that, but I'll answer that question. They gave you secant, and they said, write this function, which is secant of x, in terms of sine of x. So you've got to change this so that it's only sine. So I'm thinking, well, what the heck? What's the closest link I have to this? And I look at secant and I go, I don't have any trig identities that go secant sine. But I do know that secant is a reciprocal of a cosine. And I do have an identity that leaks cosine and sine, don't I? So what if I took that identity, the sine squared theta, if this is the one you're thinking about, and I solve for sine in terms of cosine? Solve for cosine in terms of sine, then I could replace that cosine with the sine. So does this make sense? I could solve for cosine completely. And I get cosine of a theta, technically plus or minus 1 minus sine squared theta. So I can replace that cosine with a sine. So this would be me rewriting that in terms of the sine function. You're not going to do a lot of that, so whatever, but it is a little, it's trying to get you to understand that since every trig function can be written as what? Sines and cosines, I can rewrite anything in terms of sine, and I can rewrite anything in terms of cosine. Because if I can just change it to cosine, I can replace cosine with that. And if I can change it to a sine, I could just solve for sine in terms of cosine and replace it with that. So I can always get any trig function in terms of just sines or cosines, basically by running through that identity. But you're not going to do a lot of that. Anybody else on any identity or any problem that you saw in there? Yeah. The 1 plus tangent squared theta over tangent squared theta. So 1 plus tangent squared theta. Is it theta? Alpha. Okay, the first thing that jumped into my head, it's probably not the best way to do this, but the first thing that popped in my head was that it's not a bad way to do it. That is the same thing as a what? Secant squared. And then at this point, I have one expression. So I'm trying to simplify that one expression. The two things that pop into my head now are, one of our rules is get it all in the numerator, and another rule is change it all to sines and cosines. So if I did get it all in the numerator, I would swing this tangent up and make it remember, like I can move it up if it's a reciprocal, right? So cotangent squared. And now I have this. And then if I changed all of that to sines and cosines, bless you, I would have a secant squared on the top is the same thing as a cosine squared on the bottom. And here a cotangent squared is a cosine squared over a sine squared. These cancel. And if I'm left with 1 over sine squared, what's that the same as? Cosecant squared x. So that's one way of going about it. But I like this other way a little better, that I'll show you. The other way is, since this is 1 plus that over that, couldn't I put that here? Isn't 1 plus tan squared cotangent squared? 1 plus the tan squared on the bottom is the reciprocal of cotangent squared on the top. And then what's tan squared over tan squared? 1. And what's that? Cosecant squared. So they both work, and you might, it was really tempting to change that to a secant squared because it was staring right at you. But once you start getting more comfortable with all these different ways, sometimes you can realize, oh, that's a lot quicker than going through those 3 or 4 steps. I can get there in just 2. But again, they both work. So it's not, there's no right. There's just maybe it's shorter or quicker, but there's still no real one right way. Anybody else on anything? 21, and then we're going to jump. If we have time at the end, we can come back. 21 is secant x minus sine x tangent x. So secant x minus sine x tangent x. Okay, so anybody got any ideas? Yeah, usually when I see something I have no clue, I change it to sines and cosines. Everybody with me? All right. So if I change that to sines and cosines, I'm just going to replace it with sine x over cosine x and everything. Oh, and then I can change that if I wanted to what? 1 over cosine x. So now I'm left with that minus what? 1 over cosine x minus sine squared x over cosine x. And now I have a common denominator. And if I have a common denominator, I can keep the denominator and add or subtract the numerator, which gives me this. Oh, wait, what's 1 minus sine squared? Cosine squared. So I end up with cosine squared over cosine, regular cosine, which now one of those cosines cancel, leaving me that cosine on the top. And that's probably not the only way to get there, but that is just one way. And it works. So trying to think of, oh, look at this. Here's another way. What if I did this? You had secant x minus sine tangent. So what if I didn't change this stuff on the right? I just changed the tangent part. Wouldn't I have sine squared x over a cosine x? But isn't a cosine x a secant x on the top? Right? One of your rules is factor. What if I factored out a secant x? What do I have left? 1 minus sine squared. What's 1 minus sine squared? Cosine squared. What's a secant x? The same as a 1 over a cosine. One of the cosines cancel. Still get there. I mean, there's just so many different ways you can get there. When you're taking a test, if you get stuck, don't erase and scribble stuff out, because there's a likelihood that you've done a lot right that I would give a lot of credit for, even if you didn't get to the finish line, because you're doing good processes. Maybe you just got stumped somewhere, or maybe you made a careless error that caused you to get stuck, but I could see that. And if you finally get there, I mean, it's pretty obvious. That's pretty simple, pretty cleaned up, but anyway. All right, so we are looking at a new idea today, but an identity that was on our quiz yesterday. And most of y'all did a really good job on that identities quiz. If you fumbled around a little bit or you missed, it kind of stumped because some of those are worth more than others, and you might have missed a sign and made a 17, or something like that. But be careful about that and learn those identities. Remember, I'm adding to the list of identities for Monday the double angle ones, right? And one of them has 3. You have to memorize those 3. All right, so make sure, again, I'll drop your lowest, but memorize that extra set. I think there's maybe 5 more to learn, but memorize those 5. And then remember, I'm also going to test you on the prior ones. Okay, so right here, before we even look at this, I want you to think for a second. What would you do if I asked you for something like cosine of 75 degrees? Can you, without a calculator, do anything with that? No, because it is not a unit circle value. This is where the alpha minus beta formulas have come in handy. If I can find any 2 angles that either add or subtract to get me 75, I can replace them, that 75, with that sum or that difference. And if the angles I pick are unit circle angles, like I know that 60 and 15 add to give me that, but I don't know what cosine of 15 or sine of 15 is. But I also know that 45 and 30 give me that. So these 2 things are the same, aren't they? Well, watch. If I can do this, I have an identity that's cosine of alpha plus beta. So I can rewrite this. Instead of that, I can rewrite it as the cosine. Remember your identity? The cosine of the first one. The cosine of the second one. Change that when you're doing with cosines, change it to minus, and then the sine of the first one and the sine of the second one. And I have just converted from an angle that I don't know anything about to 2 angles that I do know stuff about because they're on my unit circle. And now I can figure out, go to the unit circle and figure out what those 4 things are. So what's the cosine at 45? Root 2 over 2. And what's the sine jumping? Sine of 45 over here. Root 2 over 2. What is the cosine at 30? Over a lot, root 3 over 2. And then what's the sine at 30? Up a little. So I get those 2 things multiplied together, and then I subtract. So in your head, isn't that going to give me a 4 on the bottom? It's my common denominator. And then I'm going to have a what? A root 6 minus a root 2. And can I combine those? No, you can't add radicals that have different stuff underneath. So I'm done. And by the way, you're going to see a lot of root 6s and root 2s in your answer. Sometimes one's positive, one's negative. Sometimes they're both negative, sometimes both positive. But you're going to see a lot of that with these alpha plus betas. So what I'm doing here in number 1 and 2 is I'm trying to make a point to you that every year, it's not very common anymore, but every year somebody will be given a problem like this and they think, oh, I can just distribute the cosine in. Or they'll think to themselves, why can't you distribute a cosine? Well, the distributive property is about if you have what on the outside? A number or a variable that stands for a number. You can't distribute functions in. Like I can't distribute the sine in. Sine is just telling you to use a ratio, right? It's not an actual number. So I can't distribute a sine in. Doesn't number 2 look like I distributed the cosine in? So I wanted to show you that it's not going to be true. Like right here, if I were to do this the right way, I would pull out my cosine 120, cosine 45, change that to a plus, sine 120, sine of 45. If I were to do it the wrong way, I would distribute the cosine in and get to here. But very clearly, these are two entirely different results, aren't they? What happens at cosine of 120? Left a little, cosine at 45, root 2 over 2. What's sine of 120? Up a lot, sine of 45, root 2 over 2. And I get a negative root 2, positive root 6, all of it over a 4. But over here, what happens? Cosine of 120, I just get negative half minus square root of 2 over 2. A completely different looking answer, right? And they are not equal. So remember, you cannot distribute a function. You can't do it. If I could, think about it. Do you remember when we were doing functions and you had a function like, I don't know, I'm just going to make one up right here. Say you had that. What do you do when I ask you for f of 4? Plug a 4 in. What do you do when I ask you for f of negative 3? Plug in negative 3. What did you do if I asked you for f of banana? Plug in a banana. What do you do if I ask you for f of x plus 2? Plug in x plus 2 in it. You didn't do this, did you? You didn't go, oh, that's the same thing as f of x plus f of 2. You didn't do that, right? Well, that's a function. You can't distribute a function in. It doesn't work that way, okay? And that's what this is. This is a cosine of something. You can't distribute a cosine in. You can't distribute a log in. It's not a number. So please don't make that mistake right here. I was just trying to show you that they were not equal. Okay, let's do a couple other of these. So right here, sine of 75. Can you think of two angles on your unit circle that would add or subtract to give me a 75? And do something other than 30 and 45 just for the sake of. Do what? Think. 120 minus 45, that would work too. Although, by the way, I'm just trying to use some different unit circle values, but I would have used 30 and 45, whatever it's worth. But yeah, just to do something different, I could have said 120 minus 45, right? Doesn't that give me 75? As well as 30 plus 45? So just doing this, the rule for sine is what? Sine of the first, then what? Cosine of the second, and then you keep whatever that is. So keep the negative with the sine function. And then cosine of the first, sine of the second. Although I did see a lot of you write sine of the first, sine of the second, sine of the second, cosine. I'm sorry, sine of the first, cosine of the second. And then a lot of you wrote sine of the second, cosine of the first. That doesn't matter if you want to switch those. And then pull out your unit circle. What happens at 120? Up a lot, 45, root 2 over 2. Cosine of 120, left a little, sine of 45, root 2 over 2. What do I end up with? Root 6 plus root 2 all over a 4. Now here's what starts getting a little tricky. Number 4. I can't look at 13 pi over 12 and see two angles that would add together and give me that. Although I have a pretty good idea that it'll work. Because think about it. What common denominators are different, but when you found the common denominator, you would get a 12? 4 and 6, 3 and 4, right? And if you think about 4, you probably am not going to have a 4, but like if I had a 3 and a 4 in a denominator, aren't all the radian values that have 3 and 4s in the denominator on my unit circle? So I'm very confident that I can find two angles that do that, but it's hard for me to think that way with radians. So what I do is change it to degrees before I start. Now I will show you on Tuesday when we get back something called a half angle identity. Half angle identities are wonderful with tangents. Alpha plus beta, alpha minus beta identities stink with tangents. You're going to see that. You can do them, and it might take you 7 or 8 steps. Half angle might take you 3. So on your test, I preach this starting today, and I'll do it again on Monday and Tuesday or whatever. But I'll tell you, hey, if you get an angle that you could do with a half angle and it's a tangent, and right now I know you don't even know what half angle is, but if it's a tangent, I would do it with that because it's just going to make your life a little easier. But for now, I'm bothered by the radian. So do y'all know how to change from radians to degrees? All right, let me ask you a simpler question. Do you know how to change from feet to miles? From inches to yards? From gallons? I mean, people don't remember the whole gallons thing. I don't know. But like from all those transitions, you would use a process called what? Stoichiometry. Are y'all familiar with stoichiometry?
Yes.
Stoichiometry is like finding a common denominator in kind of a way. Do you know how, like, when you don't have a common denominator, you multiply the top and the bottom by something so that they match? That's what stoichiometry is doing, except that instead of multiplying the top and the bottom by 4, which are the exact same numbers, you're multiplying by different numbers who are actually equal to each other, but because the units are different, they look different. Like 12 inches over 1 foot, 1,280 feet over 1 mile, or vice versa, right? 4 quarts in 1 gallon. I'm technically multiplying by 4 over 1, but it's allowing the units to change. So the number's the same, it represents the same quantity, but it's different looking. That's what I'm gonna do here. This is a radian value, right? This is like radian in the numerator, a single number in the denominator. So off to the side, if I said, all right, what if I took this 13 pi over 12, which is a radian, and I multiplied it by something radians over something degrees or something degrees over something radians that would leave me with degrees. If you think about your unit circle, what pair of radian degree measures are the simplest to use if I want to make a fraction out of it? 0 would be okay, 0 and 2 pi, except that 0 makes everything 0 undefined and I'm screwed. I could use 90 and pi over 2, but that's a fraction in a fraction. What about 180 and pi? All of those work, except the one with the 0. Can't do that. But right there, all of them work. Are you with me? So what if I said, okay, if this is a radian, what if I multiply by 180 degrees over what? Pi radians. Then the radians cancel, the pi's cancel, and all I have left is degrees. And the degrees are easy for me to think about, like I did in 3. So look, I can divide out the pi's. I can divide 12 into 180. That goes 15 times. No. Yes. And then I can multiply 13 times 15, and I get 195. But look, the degree unit is left. So I changed it to degrees. Now, that's not my answer. I'm just converting this. But I'm converting it so that now when I look at it, I go, oh, now I can kind of see. So now what 2 angles on the unit circle could I add to give me 195? And 150? That works. Again, don't use 15 and 180. 180 is great. 15, I don't know anything about. So pick 2 angles. I know that, and there are other ones, right? You could use 240 minus 45 and get that. But I'm going to use what you suggested, which is 150 and 45. Same thing. And now what do I have in play? A tangent of alpha plus beta. So this is going to take a little bit of effort on these. Oh, I remember what you said. So we have, I'm going to do it over here. So I'm doing a tangent of, what did we say? 150 plus 45? All right, so let's start. Tangent of the first plus tangent of the second. This is the only one that almost looks like it's the distributive property. But then you divide it by what? 1 minus, change the sign, and then just copy those down again. But this time when you copy them down, I'm multiplying. And I think one person on this test wrote tangent of 150 times 45. And it's tangent of 150 times tangent of 45. They both have tangents on it. Now, this is where it gets tedious. I got to take the unit circle values of all these, and it's not going to be overly pretty. So one thing, by the way, on tangent, it would really help your case. Like to do a tangent, aren't you going to have to go to the unit circle and put a y over x? And then you got to simplify that. Just know this. Here are the places on the unit circle where there are special triangles, right? There's my x. There's the y-axis. Are y'all with me? Now check this out. For all of the really steep reference angles, the ones that are right there by the y-axis, or right down at the bottom by the y-axis, guess what? For all 4 of those, it's always root 3. With the exception of where the tangent's negative, which would be there and there. Now, for all of the smaller reference angles, these down these here that are really close to the x-axis, those are always root 3 over 3s. Which kind of makes sense. They're smaller than a root 3, so it's root 3 divided by 3. All of those 4. The ones in the middle are easy because those are where you went the same x and y, so those are all what? Evidently not easy. If you think about the triangle at 45, you're moving the same x and y. So if you're putting y over x, what are you going to get? 1. So all of those right there, here, here, there, and there, those are all 1s. Oh, by the way, I forgot to put the negatives in on. Everything over here is going to have a negative, and everything here is negative because it's second and fourth quadrant. And then, since tangent's y over x, what happens when the y is 0? You get what? 0 over something? That's 0. And what if it's y over x? What happens when x is 0? Undefined. So I have this memorized. So when somebody says, what's tangent of 150? I go, oh, tangent of 150, that's one of those angles real near the x-axis, root 3 over 3. But because it's in the second quadrant, it's negative. So negative root 3 over 3. And then when they ask me tangent of 45, I go, oh yeah, tangent of 45 is in the middle. Those are 1s. First quadrant, positive. So it makes it much easier, and then I copy them down to the bottom. Whatever I wrote, I copy it down again. And this is where it becomes tedious. At this point, look at the algebra this is going to entail. So the first thing I have here, I'm going to clean up. I'm going to get rid of that little chart right here. But the first thing I'm going to do, I'm going to remember this, and I'm going to recopy it. Hold on. So here's where I am right this moment. I'm just going to clean it up a little bit. And then I'm going to show you a little trick that I do all the time. Whenever I have, and I might have mentioned this already, whenever I have a fraction inside of a fraction, what could I multiply the top and the bottom by to get rid of all those fractions that are inside of the fractions? The answer to that is whatever the common denominator of everything is. What is the common denominator of that, and that? The common denominator of 3, 1, 1, and 3 is 3. Multiply the top and the bottom by 3, and look how nicely this works. Multiply there, negative root 3. 3. Multiply here, 3. Here, root 3. Already looks better. At this point, what do I have to do because of dumb algebra 2 and pre-cal rules? Rationalize that denominator. And I do that by multiplying by a conjugate, right? And then just take your time and FOIL. Here we go. On the top, negative 3 root 3, positive 3, positive 9, negative 3 root 3. That's me foiling the top. Bottom, though, are conjugates, aren't they? The bottom gives me 9. The outside and the inside cancel, minus root 9, which is a regular 3. Look, this is horrible to simplify. You're going to love the half angle on Tuesday. This on the top now cleans up to negative 6 root 3 plus 12. The bottom cleans up to 6. Is there anything I can do to that to clean that up? Divide each part by 6, which would give me a negative root 3 on the first part and a plus 2 on the next. This is literally a 3-step problem when you use the half angle. And keep in mind, I had to erase a couple steps to get it all in here. So instead of doing 9 steps on tangent alpha and betas, you do a half angle instead, and it It's just better. All right, so let me show you a couple other ways that you might see this show up in a problem. All right, so right here, somebody tell me if they think they can find that angle right there without a calculator. Do you know anything about a triangle that has an opposite side of 3 and a hypotenuse of 5? Now it's a 3, 4, 5 triangle, but again, do you know anything about, sorry, I didn't ask that right. Do you know anything about the angles? It's a right triangle, but do you know anything about the angles other than that C? It's not a special triangle, is it? Now it's a 3, 4, 5, so it's a triple, but I don't know anything about those angles. I cannot find the angle theta without a calculator. Do you know anything about a triangle that has sides -1 and 4? It's a 1, 4, root 15 triangle, but it's not pretty, is it? Do you know anything about those angles? No, and without a calculator, I have no hopes of getting them. And if I have no hopes of getting those two angles, do I have any hopes of subtracting them? No, and if I don't have any hopes of subtracting them to find that final result, I certainly can't sign it. Now, again, with a calculator, I can do all of that, but without one, what do I do? So here's what I'm going to do. Who cares about the difference? Why don't I just go get rid of that difference and break it up to where all I'm dealing with is thetas and betas, or sine of thetas and cosine betas, or whatever. So we have an identity for this. That is the sine of the theta times the cosine of the beta minus the cosine of the theta times the sine of the beta. And now I don't have any more theta minus beta thinking to worry about. All I have to do now is figure out what the triangle looks like that has a theta in it. And if I can figure out what that triangle looks like, I can answer those two parts. And then I need to figure out, what do I know about the triangle that has a beta in it? If I can figure that out, I can answer those two parts. And then once I get those 4 values in there, I can simplify it. So tell me, what do you know? Let's do it one step at a time. What do you know about thetas? I'm going to write all my theta information here. Tell me, what does this tell me? So some triangle has an opposite of 3 and a hypotenuse of 5 and an adjacent of 4. What does that tell you? What is that saying? That the angle of that is where? It's in the second or third, right? So this is telling me it's between 90, bigger than 90. Whoa. It's bigger than 90, but not quite 270. Somewhere in there. Now, wait a minute. There are 2 different triangles I could draw here, right? That could be my theta, and that could be my theta based on this. But what is this telling me? The sine is positive. And if I tried to put 3/5 here, opposite hypotenuse, I'm great. If I try to put 3/5 here, what happens? That would have had to have been a -3, wouldn't it? Because I'm going down, which means I can't have it in that quadrant. So because sine is positive, that limits me to the first and the second. The angle is in the second or third. The only place where everybody can be happy, the second. So there's my picture. And what do you know about 3, 5 sine values? There's a what? A 4 for the adjacent side. Except it's not 4. What is it? -4. Now, this brings us to the first big mistake people make on this problem. They get lazy about that part that I'm pointing at. They get lazy about it and they go, oh, sine of an angle. There's the angle, 3/5. Oh, yeah, that's a 4. And then every time they insert values in there, they're using 4 instead of -4 because they didn't place it in the right position. Be really careful about that. All right, second thing. Now that I have that, what part of this equation can I simplify? I can find the sine of the theta, right? Well, actually, I knew that already. The sine of the theta is 3/5. Not the angle, but the sine of it. What is the cosine of beta? I haven't talked about that yet. What is the cosine of the theta? -4/5. I can put that in there, although I don't know anything about beta. So let's go talk about beta. What do I know about beta? That the cosine of it is, so that's the adjacent and that's the hypotenuse. But where does it show up? Where does it exist? According to this, The angle has to be where? First or second. That's what 0 to 180 means. But wait, triangles here would not have negative cosine values, would they? I mean, think about it. If I draw adjacent and then hypotenuse, that doesn't make sense. I don't go to the right -1. It can't exist here. But what if my triangle was over here? I could go adjacent, hypotenuse. That does work. Now, is that a special triangle? No. So what do you have to do to find that missing side? You have to pull out your Pythagorean theorem. I'll do that once, but if you can do that in your head, no problem whatsoever. But right here, you'd have to say, all right, 4 squared equals, I guess I could call it y squared plus -1 squared. So I take that 16, that ends up being a 1, I subtract that 1, and then when I get 15, I square root both sides. So that y is root 15 right here. And since it's going up, I can leave it as a positive. If it were going down, I would have to change it to a negative. Now that I have angle B set up, can I answer questions about angle B? The cosine of B I already knew technically from the original problem. But now what is the sine of angle B? Root 15 over 4. You got everything plugged in. Can I clean it up? -3 is what the top would be here. +4 root 15, which would be the top over here. And both of them are over a 20. You tracking with me? I have never not had a problem like that on my test. Just saying. Yes.
Wait, can you go over where you got the root 15 over 4?
Pythagorean theorem.
Yeah.
I only knew these two values, so I was missing that y value. So I just wrote out the Pythagorean theorem, 4 squared equals y squared. You pick any variable you want, plus 1 squared, -1 squared. And then I just solved for y. I took that 16, that's equal to 1. I subtracted a 1, got 15, square root of both sides. So just Pythagorean theorem for the missing variable. And then I put it in there as a positive because I was going up. If I'm ever going left or down when I do that, I make it negative.
But also in beta, how did you know that it was a -4? Sorry.
Well, remember, if such that's a good question. Better than you might think, actually. Check it out. What if I did the math on it? You know, right here, technically when I do the math, what do I get for y? When I square root both sides, don't I get plus or minus root 15? So pick the one that makes sense. Up, root 15. If I were to do Pythagorean's theorem here, it would be 5 squared equals 3 squared plus x squared. You would take that 25, you'd subtract that 9, and when you square rooted that, you'd get what? Plus or minus 4. But you pick the one that makes sense. If I'm going left, -4.
How do you know it's going up?
Because I drew the picture right there.
What did you write?
Well, then it's not. Remember, yeah, I know. That's why we don't go to the bathroom. Gotta hold it, man. Right here. 2 things. Sine is positive. Sine's only positive here. Right? First and second. Angles, 90 to 270. The angle only exists there.
Oh, okay.
What can they can only be true in both where? In the second. Right? Second one. Cosine's negative where? Here. Angle 0 to 180 here. Where can they both be happy? Only there.
Thank you.
Yep. All right. Jump into another one. We're getting a little low on time. Oh no, 6. This is an example of where I'm giving you an identity, but instead of just having thetas and betas or alphas or whatever in there, I got some numbers in there. Now, at first glance, I'm like, ooh, I can do cosine 30, sine of 30. But it would still look terrible, wouldn't it? You'd still have sine of 230. I don't know that. Cosine of 230. I don't know that. But what is this? Does this look familiar to you? It's a sine of what? Alpha minus beta, right? So that would mean that this is the same thing as the sine of the alpha, the 230, minus the beta, the 30, which gives me sine of what? Well, that's a whole lot more simple than it used to look. And now, are there 2 angles on my unit circle that could add or subtract to give me 200? Well, you can look all day, you're not going to find one. I can get 195. I can get a lot of things, but I can't get 200. And if you go, what about 150 and 50? Again, they got to both be on the unit circle, right? And 50's not. So if I can't go any further, I'm finished. And if I had a calculator, I could have just typed the original thing in and found the approximation. We're talking about without a calculator. No. What about number 7? Does that look familiar to you? Because right now I can't do anything with 140 and 80. An alpha minus a beta. So if that's a tangent of an alpha minus a beta, and the alpha is the 140 and the beta is the 80, what does that clean up to? And then what do we know about tangent when the angle is close to the y? √3. See how easy that is? And you don't have to go and go, oh, let me get the y value, the √3/2, and put it over the x value, the 1/2, and then cancel. It just makes it so much easier when you memorize those. Steep one's √3, shallow one's √3/3, one's in the middle 1, undefined up and down, 0 left and right. You just do that for tangent, it makes it so much easier in the long run. And then remember, if it's in the first or third, it's positive, second or fourth. What about number 8? I can't do anything with 2 30s and 20s, but wait, is that a recognizable identity?
Yes.
Good. That's a cosine of an alpha, opposite sign with cosines, minus that beta. So this is the same thing as a cosine of 210. Oh, I know about 210. 210's what? Left a lot. To get to 210 right there, I'm going left a lot. So negative square root of 3/2. Number 9's a lot like that one I did before. In the interest of time, I'm not going to do it, and I'm going to jump to number 10. So this is a little bit different, but I just wanted to throw it at you. You're asked to solve. Now, so far when somebody's asked you to solve, you've had stuff like sine of theta equals 1/2. Sine of theta equals 0.527 or whatever. Now they're giving you just some weird equation. So out of sheer desperation, is anything jumping out at you? Since we are in the alpha plus beta, alpha minus beta section. So I have literally a sine of something plus something and a sine of something minus something. So what if out of desperation I went, well, maybe I could just do that. Okay, maybe I can't distribute the sine in. That doesn't work, right? You can't distribute a function in. But maybe I could rewrite it. So isn't this right here the same thing as the sine of the first times the cosine of the second? I'm just doing this first part. Plus the cosine of the first times the sine of the second. And then couldn't I add that to this other one? So there's the first one right here. And then I could take the second one and put it right here. What is the second one? Sine of the first, cosine of the second, but this time minus cosine of the first, sine of the second. And this whole thing is equal to 1. Now, you see anything you could do? Those are opposites, right? See anything you can do? What do you notice about what's left? Same thing. So you have 2 of them. You didn't have to. You could have done something else too, but whatever. You see anything you can do at this point? Okay. You see anything else you can do at this point? Whoa, that's cosine of pi over 3. Literally. This right here is not a 3. This is a ratio. Cosine of pi over 3 is a ratio, right? You know that. A cosine of an angle is a ratio. So don't cancel part of the angle out, right? What is cosine of pi over 3?
60.
What's cosine at pi over 3 is 60. What's the cosine of pi over 3? By the way, that is a very common error. People do that. I'll go, what's sine of 7 pi over 4? And they change the 7 pi over 4 to the angle and they stop. You are welcome to do that. to change a radian to an angle. I would just get used to the radians because in 2 years, then I'm going to use degrees in calculus. So get used to it. But don't change it to an angle and stop because I want to know what the cosine of it is. What is the cosine of pi over 3? 1/2. So I end up with sine of x times 1/2 equal 1/2. Then what could you do? Multiply by a 2, sine of x equals 1. That's why I wouldn't have divided by 2. I would have changed that to 1/2 right there, and then the 2's would cancel. But it doesn't matter. It just looks a little uglier here. Now you can solve it. You got to a nice simple, and you don't even need an inverse. Where on your unit circle do you sine an angle and get 1? Or where is the y value 1? What does that suggest? That my angles need to be in what? So where does it equal 1? Pi over 2. If you said pi over 2, I didn't mean. So my angle is pi over 2. Just wanted to throw that out there, let it marinate a little bit. I don't see a lot of that showing up on your test maybe, but. All right, we're going to call it a day. Anybody go anywhere interesting other than Universal?
I'm going sailing.
Sailing? Ocean sailing?
I think so. I know about it yesterday, but yeah.
Huh. I sailed in Chesapeake Bay once.
I went on a big sailing trip with Boy Scouts a while back.
Yeah?
I was out with the Keys.
Now you can keep that quiz too. And don't show up Monday going, oh crap, I forgot the quiz, or it's gonna get another beating. Or if you didn't get a first beating, you'll get your first beating. Don't let that happen. Yeah, Monday, all I'm doing is adding double angles. And then everything else we've already been quizzed on will be 1 point apiece. The double angles will be worth a little bit more, kind of like the alpha plus beta will worth a little more. All right. I was literally anticipating you saying, set a reminder for Sunday, April 4th at 10 p.m. I was waiting for that, but yeah, 4 p.m.
I don't want to start too late.
Ari, make some flashcards, take them to the beach, to the blow-up pool in the back, whatever yours you're doing. Just start looking at them slowly, let them start marinating. The more you know them, the better you will be.
Oh, I don't know how to type it out. I've never typed a minor on my phone. I've always used Siri. Anytime I try to type it out, it doesn't work.
How's it going?
Commissioner,
Made it.
Yes. You off 7?
Yeah.
Nice.
Yeah. Usually we have practice, but
Not
we don't
today.
today. So
'Cause you're in charge.
OJW today.
No. Who? Oh, Jada.
Yeah.
Sam here?
I doubt it.
Hold on, hang on. I didn't have any self-worth of totally.
who's in Power School?
Just fail. Yeah, or say, guys, I got a video, just go watch it. I've totally recorded this period already. That's really a good idea. Guys, go. I'll sneak you out the back.
Hey, Mr. Hurry.
How are you?
I'm
Oh,
good.
yeah.
I'm good.
Nice. Added entertainment?
Oh, yeah. So I'm pretty worn out, so.
Well, it'll be tough finding a seat in here. With all 7 of us. Well, no J-Dub, 6.
No Sam.
Sam's definitely not here. Is that right?
I think so.
What about Kieran?
He was here earlier.
Yeah, he was here when I went.
About
Well,
Thomas?
JW was here during lunch.
But he checked out last period.
So it's just,
Kieran was here first period. I knew that.
He was here third.
A lot of checkouts. Tell you what, you don't have to have perfect attendance. That spring break just grows and grows.
Yeah. My absence is excused, though, so.
What did you have again?
For Best Buddies, some of us went to the mega fields and
That's
played
right.
soccer with the elementary schools, the middle school, and then like the high schools from Pinson Valley, Clay, and Pleasant Grove. So, yeah. So I had to rep high school teams. So I was running around everywhere. I'm exhausted. It was me and Coach Matt.
I used to ref soccer as a job.
I'm technically certified, but I like don't do it. So.
What's up, man?
How's it going?
Man, it's going all right.
Oh,
Man, it'd be a good day for an off day, huh?
It would. Xander and I were just talking about that.
15 minutes.
I got a video.
getting back.
Good old, I could just walk you to your cars, tell you to watch the video, call it a day.
We do that as well.
Yeah.
Or we can go play some kickball.
We could go play some.
We could indeed play kickball.
1, 2, 3,
Oh, that's so sad.
4.
You lost charge.
So you said there's no Sam?
What?
I don't think
chart.
he's been here all day.
Is Kieran here? I saw him one.
He was here this morning, but he's usually like the last one in.
He stands right outside. He was talking to Owen.
Oh,
Yeah, it's a small chart.
yeah. I wish we could play Linky in here. Oh my gosh.
That would be fun. We
Charlie.
had to give him. We had to give him back to the center stage. She has a 7th period.
Oh.
Yeah, we were in upstation. Yeah. Both me and Eli took to do a bunch, trying to get your days to come. Oh dang! No, because I was talking about Days in LA, and we came in. So we saw my stage, and she's like, "Are y'all giving Linky back?" And I couldn't figure out what she meant.
Yeah, because me and Eli were like, we're gonna get Nathan Gates from here.
Yeah. Y'all are a lot better than I was. I was really you couldn't help me that good.
I'm sorry, Linky. They read out 4 clues, like little questions, and the answer to each one, is like linked to like one answer. So like on one we had it was like The major way to cook eggs other than scramble and boil is fry. And they don't say you keep them in your head on. Or then one was like, finish the sentence. With this ring, VI blank, and it was wet. And so wet and fried, and it was like days of the week. There's 4 of those.
And then one was like,
It's hard.
normally you're eating like a cookie, a cinnamon roll. Y'all made spaghetti,
We had a big Italian meal yesterday. This is leftover.
cold spaghetti.
I microwaved it.
These are done, dude.
All right, come on, let's go. Let's get this over with.
I was like,
So strange.
Yeah. You want to get closer, or are you good?
Yeah.
It's up to you.
I was just like, I don't know where anyone said.
I was like, it's 45.
All right. I am on. Actually, I got this pulled up. I'm on page. Whoa. Strange things are happening today.
I didn't get what to say.
Look at that.
I didn't do it.
Page number gone.
Huh.
It's weird. 53, I think. Try 53. Come on, guys. Oh, out of it.
Yes.
Are we still having that test on Wednesday?
Yeah, boy. Girl.
And this is probably like the lowest attendance rate, 4 out of 7 in the school.
It's true. Of any class.
That's what, like 57% attendance?
I had a pretty thin one last period. I bet there's some senior classes that are.
Yeah.
Like there's an AP studies 6 periods, and like 2 out of like 5. So 40.
Yeah. All right, guys. So I've given you all these rules for certain situations, but there are a lot of situations that really don't have rules that you need to start thinking. And the thinking, those are the questions that people tend to miss the most. Because a lot of people just I want to be able to look at it and know what to do. So when you look at it and you know what to do, great. When you look at it and you're like, what the heck? Then just slow down and start thinking for a second. So I'm looking at this first one. And by the way, don't forget, we mentioned this yesterday. Don't forget, if I can graph it, which I can a lot of the time, graph it and take a look at it. So right here, I've got the limit of 52 e to the negative x plus 3, and I want the limit as I go forever to the right. Now, right here, if I'm adding 2 different things, can't I take the limit of each one? So I look at the first part. Now I could graph this whole thing actually, but I'm going to show you a couple ways I would go about doing this. So the first thing I would do is thinking about it as 2 different limits. The limit of that plus the limit of that. So I'm going to graph 52 e to the negative x. How do I graph? 52 is just a big coefficient. But how do I graph an e to the negative x?
Would you flip around e to the exponential?
If I negate the x, I flip over the y. And it makes sense, right? I mean, think about it. If I were to plug a big number in there, it gets really tiny. If I plug a big negative number in there, it gets really big. This exponential function does this, right? So what's happening as I approach infinity of this exponential function? Getting closer to 0. Now, the limit of the constant's easy. What's the limit of 3? 3. So 0 plus 3 is 3. Now, you can think about it graphically. Here's another way you can think about it. I could also just plug an infinity in there, right? I mean, I know it's not really infinity, but let's just say I did. I mean, infinity is not really a number, but let's just say I did that. I tell my calculus kids, when you see this, the reason why it's hard is that negative. So if I just took the negative infinity and made it a what? E to a positive infinity, then what is happening with this fraction there? It's approaching 0, right? Because the bottom is getting huge. So if that's approaching 0 and I add it to a 3, then I'm getting 3. So that is probably, and that is a very common looking AP question. And it usually comes at the tail end of a longer question. They're like, okay, well, if that's your rate of growth, what's the limit as you approach infinity? All right, what about this thing? If I plug in infinity in there, what happens to a log curve as I go forever to the right? It's what?
Flattens out.
Does it ever flatten out?
Oh, no.
So
keeps going
it's
down.
going to infinity. Now, it may not be going up as fast as it's going to the right, but it is approaching infinity, right? What's happening to the exponential function there? It's also approaching infinity. So I have an infinity over an infinity. Well, and you're thinking this, I think, but you're thinking, wait, but that infinity isn't growing as fast as that infinity, is it? So not nearly, not even as fast as a linear. It's really slowing down. So the exponential function is growing to infinity more quickly than the natural log. So what's happening to the size of that number? It's getting smaller and smaller and smaller. Yeah, because the natural log curve that's in the numerator is doing this, right? It's getting bigger, but it's not getting bigger very quickly. The exponential function in the denominator is getting quicker really quickly, isn't it? So since the bottom one is growing faster than the top one, this is kind of like having an infinity on the top, but like a bigger infinity on the bottom. The size of that fraction is reducing, right? And if it's reducing, it's going to zero. Now, we said that there's going to be this rule called L'Hopital's rule, that if you ever got an infinity over infinity, you could take the derivative of the top and the bottom and redo it. Guess what? When you take a derivative of that top, that natural log of x, you actually get this. You end up getting 1 over x. When you take the derivative of the bottom, you get e to the x. It's a rate of change. It's a slope or rate of change. And if I simplify that, I get this. You get 1 over, to divide by a number, you multiply by its reciprocal. So I get this. Now, isn't it really clear now to see if I put an infinity in, the top's getting huge, the bottom's not growing at all, it's going to zero? So L'Hopital's rule would help you, but I don't think it's more helpful than just looking at it right now and going, it's growing faster on the bottom. Look at number 3. Now, a lot of people write D&E on number 3 because D&E on number 3 would be the answer if the 2x wasn't there. If I said, what's the limit of a sine curve as you go to infinity? Well, I'm oscillating between what? 1 and -1, 2 fixed points. And if I'm oscillating between 2 fixed points, am I approaching a y value? No. And they quit on this and they say, well, it's got to be D&E then. But it's not D&E. And it's not D&E because there's a denominator that's doing what? Going to infinity. So even though the top is oscillating between 2 fixed points, the values of the numbers on the top are very what? Small. And the values in the denominator are what? Huge. So if I have really small denominator and a really small numerator and a really huge denominator, what's the value of this becoming? 0. Now, it would actually be approaching 0 from both sides. Like it would actually going positive to negative to positive, negative, positive, and actually going through 0 too, because x would be 0. Now, you'll never see this question on my test, nor on an AP test, I don't think. But let me show you how I could really make it ugly. What if I gave you this? I just want you to think on this. Now what's happening?
Getting really big on the top.
It's getting huge on the top, but the bottom is what?
Small.
Stuck between numbers, between there and there. So what's that growing towards?
Infinity.
Is it?
Could be infinity or
Would it
negative.
be D&E?
But yeah.
I'm hearing all truth.
It can't be.
For values that are positive on the bottom, it's going to infinity. For values that are negative on the bottom, it's going to negative infinity. But for values that are 0, it's undefined. So if I were to graph this, you're going to see this. It's shooting up to infinity as it's going through the positives, and then it hits a 0, undefined, asymptote, something. Then shooting down to negative infinity as it rotates through the negatives, hits a 0 again, undefined, and it's going. So clearly, is it approaching a single y value? No. D&E.
Does it look like a tangent?
I want to say yes, but I honestly don't know if I've ever graphed it. Take a look. That's not going to be powerful. I need more horsepower.
Series.
Let's see. Menu, window, trig, tab, 2 to the x. It does not like stuff like this. Divided by sine of 3x. Enter. that makes sense. So not really a tangent, almost looks more like a secant kind of looking thing. But you see all that. They don't have the asymptotes, but you can see it shooting up and then coming down. So you can kind of see the asymptotes. So it actually looks a little different than I thought it would. Oh, wait. That's the negative infinity. Negative infinity starts looking like it's more like zero, but still has those asymptotes. The positive infinity, I'm going to have to really, let me open up this window. Window settings. Let's go to 100 and negative 100. Oh, still thinking. Okay. On window settings. Yeah, it's not even worth graphing that. Let me see. I can go to make it look a little better. How about to 15? Here, I'll show you in a second. There you go. So you can see it
Further and further.
as you go to the right. Yeah, it looks like it's getting further and further away, but it still has that in between each of these. There's a VA. There's a VA at all the zeros, right? And then it's just positive, negative, positive, negative. Yeah. But anyway, I haven't seen that on an AP test. Nothing. They don't, especially not an AB, because you're limited in what you need to do with low P totals on AB, and in BC you have a lot more indeterminate forms, is what they call them. We only have 2 in AB that we have to worry about.
You're limited.
Yes, you're limited with your limits. All right, what about number 4? But what if I did this? Now,
Wait, Mr. Head, the value on the bottom is so big. How could that ever surpass at the top?
what if I did that?
No, it has to be getting bigger on the top. No way.
Check it out. We're going to do it.
Even we.
If you guys can hang around to the bitter end, we can have some fun with the calculator. All right, menu. We'll start with the standard window. And we're going to go tab, fraction button. What do I got on the top?
It was 2 to the x.
2 to the x power. And on the bottom, we're going to go x to the 1,000. So here we go. No, that's not what I'm doing. I'm doing 2 functions. We're doing 2 to the x. Whoa, what the heck? I don't want a relation. Okay, so 2 to the x is my first function. There it goes. And for the second function, x to the 1,000. Oh my gosh, so much bigger.
Vertical, Mr. Murray. Do you think exponential growth will become vertical?
Never.
I find that very vertical.
Okay, so window 4 settings. Let's go out to 100. Oh, I don't need to see that. Let's go out to 100. And I don't need to see that. And let's go up to 10,000. See the red line? Menu X. I'm not going to need a lot of X, I don't think. That red looks awfully steep. but the exponential starting to creep. So what about, what if I went, I'm gonna have to go further. How about, ooh, starting to get aggressive.
Whoa.
What?
We were right, X to 1000 is
That
larger.
was clearly. It does not exist.
It's uncool. Oh, well.
Way too up.
Maybe I didn't go X to the 100th. Oh, what did I do?
X to the 1000.
Oh, yeah, that was a little too aggressive. Well, it is true.
Right.
But to show you this, gosh, didn't change a lot, did it? Man, it will not let me go that high. So that's unfortunate. Having a little trouble with that X to the that's unfortunate. Gosh, even X to the 10th.
So they're the same.
They equal out.
Well, I don't, this is weird to me because you can see it there.
So it's between X to the 5th and X to the 2nd.
Yeah, that actually works. There's an X to the 7th, and you see it catching up. It catches up. I could swear we picked a bigger number than that. It's been a long time, and that's why, because it takes 10 minutes. But I can't believe I can only go that high, because I thought you could go, I know you could go to 990. I can go to the 999 decimal places to the right. But I guess when I put X to that, to the what 1 billionth or 1 trillionth power, that's a lot bigger than that. A second you put a 2 in, and it just freaks out. So interesting. But yeah, you can see the exponential eventually eclipsed the power function. And that would be true on all of them. But anyway, oh well, that wasn't as pretty an explanation as I thought. So anyway, back to what we were doing. If you're looking at this, it doesn't matter whether it's X to the 10th, X to the 100th. This is eventually going to outgrow it. So what do you get there? Infinity. But what would happen right here, this is not the problem, but what would happen right here if I said negative infinity, if I made the limit go to negative infinity? Yeah, that function is exponential. As I head to the left, the top goes to 0. The top ends up being a huge positive number, right? That's even whether positive or negative goes to 0. All right, what about this? This is a great little AP question. It might be an actual AP question that I stole, where you see these little, somebody was telling me they're not going to do this in Latin anymore, but I've heard no indication about, where they give you something and they go, which of them are true? So you're checking these 3, and I think they're throwing them out because you could be right on 2 of the 3 fronts, but still miss the problem. So is this true, that true, or some combination of them? So the first thing says, is the limit of this h function, does it exist as I approach 4? Well, how do I check approaching 4? The left and the right. What equation or equations represent left and right? The top one only represents left and right because it's not equal. and not equal in piecewise functions means greater than and or less than, or greater than or less than. So right here, if I plug a 4 in, I get 0 over 0. So what does that mean? So my factor cancel out the x minus 4, so I'm left with an x plus 4, and I redo it and get 8. So the limit existed, right? Does the value of h of 4 exist?
Yes.
Yeah, it says that at 4, it's 8. So the value existed. Well, is it continuous there then?
Yes.
Why? Because the limit and the value existed both and were the same. So all three of these are true, and you just checked the 3 points of continuity, whether you realize it or not. All right, number 6. I thought this was a little tricky. I have put this on a test many a time. But so can somebody look at this in the context of limits? What is happening with this chart? Take a good look at it. Don't wait for somebody else to think. What is happening with the x's?
They're approaching 1.
Are they approaching 1?
Well, they're getting closer and closer to 1, but by fewer.
They're getting closer and closer to 1 from the right side. Do y'all see that? Right, I was at 1.1. I started pretty close, right? 1.1, 1.01, 1.001, 1.00. I'm getting closer and closer to 1 from the right. Look at these answers. That limits you already to just D and E, doesn't it? Closer and closer to, no, not even E. You're done, D. The only one that's approaching 1 is from the right is D. But let's go a little further. What's happening to the Y values? They're getting closer to 1. So the limit of this function as I approach 1 from the right side is 1. That's what this is saying. Now, you could have an argument by saying this. You could say, who says you have to read it from the right? Couldn't I say the limit as I approach 1.1? I could be approaching 1.1, right? But if I was approaching 1.1, I'd be approaching from the what? From the left side. And what would my limit be then? 0.9. I just don't see that as an option. But I guess you could argue coming this way, I'm approaching a 0.9, right? Maybe. But that's not an option right here. So I'm going to go the other way. Stick with that. All right, you saw this problem number 7 on your test. Remember it? What does the graph look like as you approach a 5? And a lot of you got it right, a lot of you missed it. But if I plug a 5 in there, I get 0 over 0, and you go, oh, it's a hole. But if you cancel out those common factors and redo that, plug it back in there, you get what? 2 over 0, which is a VA. And the VA trumps any mention of a hole. And that will only happen when you have like a perfect square on the bottom, like an x minus 5, x minus 5. What about number 8? We've done a problem like this before, but let's do it again. It says, find a value for the constant so that that function's continuous. Now let's think for a second. What is a continuous function? What does that mean? Continuous means
The limit is a function of E.
that's continuity at a single value. But if it's an entirely continuous function, polynomials are examples.
Any limit will be the same as any.
So what does that look like to you? If I tell you a function's continuous, it goes
There's no break.
no break, forever to the right, forever to the left, no breaks. I look at the bottom function, I see a line. If k is a constant, then that's just a linear function. Linear functions are continuous. I look at the top function and I see a sine curve over a line. Sine curve's continuous and lines are continuous, but what? In the denominator, that x could not be what?
0.
Well, I'm not worried about it because it doesn't exist at 0. So the only thing that could go wrong here is if the top function, which appears to be continuous everywhere except at 0, and the bottom function might not fill in the top function's opening. But if it did, and you have control over that, you could make this continuous. So bottom line is, I'm talking a lot, probably more than I need to, but I want you to understand, I could give you a question, like for instance, what if I said, my pen's good. What if I said, find the value for the constant k that would make this function continuous, and I put a tangent right here? What if I had a tangent where this sine is? Well, there isn't a function that'll make this continuous. What do tangents look like? That, right? You got vertical asymptotes all over the place. There's no way I can manipulate this K value at only that point and fill in all of those gaps. In fact, you can't make a vertical asymptote continuous anyway. You can make a whole continuous by filling it in, but not a VA, right? You can't fill in a point. That thing's just climbing forever. So in this case, I would say there is no K value that makes this continuous because look, that's not a continuous function. But because I don't have that, because I have sine there, and I'm like, wait a minute, this would be continuous everywhere. This would be continuous everywhere. Let's see about where they connect. So how do I ensure continuity at 0? Well, let me think. The 3 points of continuity, which are what? So the limit of the function must exist as I approach 0. The value of the function, which is this, right? Must exist at 0. Right? So the limit of the function exists. Sorry. Let me do this. The value of the function exists and they're equal. Limit exists, value exists, and they're equal. So what's the limit of that? 4. It's one of my rules. What is f of 0? 3k plus 2. So what's k? I am literally just checking my 3 points of continuity. And AP will ask that question or a derivation of it, literally a derivation there. They'll ask you about differentiability, which is a derivative of that. Unintended. But anyway, this is one that shows up a good bit like that. All the rest of these are more practice with limits, but I'm going to show you some other ones. Look at number 12. How do I do that limit? Well, first you plug the 0 in before you get started, right? Because you might get an answer. But when I plug a 0 in, I get 1 minus cosine 0, which is 1 minus 1 over 0. So I get 0 over 0. So what does that tell me? There's a hole, which means there's probably a limit, right? So what do? If I split it up, I would get this. Now, I will say that many of people before you have gotten this problem right through bad logic. What happens now when I do this? Now, what do I get when I plug a 0 and I get DNE minus DNE?
That's 0.
Literally, the answer is 0 here, but it's not because DNE, like this is 1 over 0 minus 1 over 0. DNE minus DNE is not 0. That is terrible thinking. Okay? You were just very lucky. All right? And yes, sometimes it's better to be lucky than good. But that is not a true statement. But this was one of the ones I said to memorize. If you go back and look at your formula sheet, there was all those little trig rules, and at the very bottom in the middle, there was that. I mean, it might have been cosine x minus 1 over x, but all you do is factor negative out. But anyway, that for now, just memorize that it's 0. And then when you learn L'Hopital's rule, you could take the derivative of this, and when you take the derivative of it, you actually get a 0 over 1, which is 0. So for now, you're just going to memorize. When you see that, oh yeah, that's equal to 0. Number 13, if I had $1 for every time I saw that answer as 2, I would have tens of dollars. Okay, but I don't get 2 because I don't have, first of all, I did not get 0 over 0 when I plugged the 0 in. What did I get? And the only time I go and take my rules, which is 8 over 4, is when I have a something x over a trig function of something x, and I don't have that. I got 8 over 0. What does 8 over 0 mean? I got a VA, and what happens at a VA when the bottom's not squared?
They split.
It's DNE. It's DNE every time, unless I'm just checking from one side, and I'm not checking from one side, DNE. All right? I'm just doing some of the trig ones. What about, okay, this file is just totally wigging out. Open that back up. It's erasing page numbers and all kinds of stuff. Martina, what page is this?
4.
Pretty good to be like,
All right, oh yeah, look at this one, number 15, guys.
you're my
Right here, number 15. Tangent of pi over 3, limit of exponential 0 of tangent pi over 3 over 2. If I had $1 for every time I saw somebody write pi over 3 over 2, wait a minute, I'd have tens and tens of dollars. But right here, I don't have an x to even plug in, so what does that make this?
Just tangent.
That's a constant. And if it's a constant, what is the limit of a constant? The constant. So literally, my answer is tangent of pi over 3 over 2, except I do want to simplify it. So what's the tangent at pi over 3? Root 3, carry the 2 over. So that's that. But if there's no x in there, guys, don't make junk up. I didn't forget it. I've literally had people put the x in there and then write pi over 6. I'm like, what are you doing? Number 16. What do you got there? What happens there? First plug the 0 in, and I get 0 minus 0 over 0, which is 0 over 0. So what does that mean? Holes? Well, I can break it up like that. And then I have sine of 4x over sine of 2x minus 3x over sine of 2x. Couldn't I take the limit of each of these separately and then subtract them? What's the limit of the first one?
2.
Yeah, 2 or 4 halves. What's the limit of the second one? 3 halves. What's 4 halves minus 3 halves? 1 half.
And wait, so when you have the x's over the x's, it works the same whether or not you have like a trig on both on top and bottom.
You could have a trig of anything x over a trig of anything x, and it doesn't have to be the same trig. That's why I'm writing that. You could have a trig of anything x over anything x, or you could have anything x over a trig of anything x. And if you are seeing those and you get 0 over 0 when you initially do it, then, sorry, that's supposed to be a b, then a over b.
Is that when x is approaching 0 only or 8?
No, when x is approaching 0. So if the limit of these, or whatever, any of these, and you got 0 over 0, then you can just take the a over b's on each of them. All right. What about number 17? Ooh, it's a tricky one. First time you're going to see one of these. I usually make these bonuses. Okay, so we don't deal with cotangent, secant, or cosecant. So that cotangent on the bottom, what does this become right here? Good. The 2 stays on the top. It's not inside, it's outside. And I end up with what? Tangent x, tangent 3x. So plug the 0 in, and what do you get? 2 over 0. What does that mean? There's a VA. What's this limit?
So do you flip the co-functions before you check for 0, 0?
Well, they're not always co-functions, but cotangent, secant, and cosecant, yes, before I apply them. Because if I plug zeros in a lot of those right now, I get DNEs and it throws me. Why? Yes. This is not squared, right? But think about it. The reason why squared does what it does, think about it from this perspective. Let's just say I had an x minus 1 squared on the bottom, right? The reason why it does what it does is because if you graphed, let's just make it super easy, x squared. The reason why it does what it does is because you have an x function and another x function. I'm making them look a little different so you'll see it. From the right side, they're both positive. From the left side, they're both negative. Plus over plus, plus over plus. Now, squaring it does the same thing, right? Squaring them makes it positive. But the point is, from the left side, I had a negative times a negative. Well, same thing here. What's a tangent of x look like? At 0. What's a tangent of 3x look like? From the right side, they're what?
Negative.
Both positive. From the left side, they're, and if I'm multiplying them together, it doesn't really matter. They both end up being positive. So if the both sides of this VA, you know it's a VA, are positive on the bottom, and you know the top's positive because it's 2, then these have to be doing that. And you gotta go with infinity, not D and E.
What if it was like sin X or like cosine instead of that?
Okay, great question. So she's saying, what if it's sine and cosine as opposed to, or tangent and sine or whatever? Think about the graphs. So like, what if I had given you, I want to come back to that one. What if I had given you this? So I'm just adding this in here. What if I said the limit, I'll just start you right here. What if I said sine of x, tangent of x? Because that's good. And we'll make it tangent of 4x. Well, what's the sine curve look like? What's the tangent curve look like? From the right of 0, from the left of 0. They're both positive, aren't they? Negative, negative, positive, positive. So if they're both, you know there's a VA because you got this. But you know that top's always positive. Now you know the bottom's always positive. Must be doing that. All right, what if I gave you this one? Now let's think about it. You plug a 0 in there, you get 4 over 0, don't you?
Yeah.
Right? Let's think about it. What's the sine curve look like? What's the cosine curve look like? So from the right, it's both positive. Ooh, from the left, it's negative. So from one side of that VA, from the right side going up, from the left side going down. So if you wanted to consolidate all your thoughts, it's really when you have two sines in there or two tangents in there, because what are two tangents really? Two sines on the top of cosines, or a tangent and a sine, because what is a tangent? A sine over cosine. So if I have this, I only have one sine curve. But if I had something like this on the bottom, isn't tangent of sine x the same thing as a sine of 5x over a cosine of 5x? Right? So that's like a sine. And if I had two tangents, aren't they sines over cosines? So it's like a sine. So whenever you have two sines, two cosines, or a sine and a cosine, yes, it's almost like they're squared, even if they're not squared. And I usually reserve those to be in bonus questions because I kind of like them. They make you think a little bit, but I haven't seen those on a test. All right, for all the marbles, the gold star, number 19.
One minus cosine squared x is like sine squared x.
Well, first you got to plug the 0 in.
Right.
Plug a 0 in, natural log of 1. Plug a 0 in there. Plug a 0 in there. 0 over 0. So it appears like there's a hole. And you would think if there's a hole, there's a limit, right? Guess what? Limit does not exist here. How do I know that?
Oh.
This is how I know it.
Did you watch this in first period?
No,
You're special.
we're special because we're all really tired.
Who did competitions the other day?
We did. That was,
Volume does not exist apparently either.
Try to solve the problem in front of you. Felt stupid doesn't make you any smarter.
Find the
I haven't
limit
seen
of
this
this
movie yet.
equation.
Calling somebody else fat won't make you any skinnier. Calling someone stupid doesn't make you any smarter. And ruining Regina George's life definitely didn't make me any happier. All you can do in life is try to solve the problem in front of you.
The limit is -1.
Oh crap, I lost.
That answer is incorrect. Now we are in a sudden death. If Miss Heron can answer this problem
hasn't seen this?
correctly, we have a winner.
Limits. Why couldn't I remember anything about limits? Limits. That was the week Aaron got his haircut. Oh god, he looks so cute. Okay, focus, Katie. What was on the board behind Aaron's head?
Has nothing to do with this
The
problem.
limit never approaches anything. The limit does not exist. The limit does not exist.
Our new state champions, the North Shore Mathletes.
Go forward. This guy, watch this guy. It's awesome. Get some.
How do you like me now? You like that? Yeah, get some, get some.
Dude, if that ever happened in my lifetime, like if we went up to get an award and one of you were like, grabbed the trophy and went, get some, I would roll. I would laugh so hard. Oh my gosh. I can't believe nobody has done that.
Rip their shirt off.
I mean, there's tons of Indians. Any one of them could have stepped up over the years. It would have been, dude, the house would have been brought down.
Wait, but do people actually watch the awards?
Well, we haven't gone. You guys don't go because they don't make you go. But yeah, there's usually like all the people that traveled from out of town,
Oh,
they're all in there. Parents come sometimes. We normally have like 3 people because nobody comes. But it would be awesome.
You do one more year to make that happen.
Yeah.
We'll come to all the award ceremonies. You can make us come so that can happen.
Yeah. Anyway, that's the actual problem. And it had nothing to do with whatever the heck she just did. 1/x graph or whatever she had behind Aaron's head. But anyway, I don't even know if I remember doing it, but I've graphed it and it definitely does not exist at 0. Anything else that jumps out at me?
Can you like put that on the test, the
Yes.
first period, or did you tell them that like this is the Mean Girls?
I did tell them it was the Mangers. We just didn't look at that. Another thing that was on your notes that I didn't mention, it was actually on your other test, but I erased it for y'all. I got rid of that problem, which is why we were misnumbered a little bit. But this is how AP calls holes. They might refer to it as a hole, but most of the time refer to it as a removable or a point discontinuity. So a removal, you're like, how do I remove it? It's a hole. Well, you just plug a value in there. So do I ever do that? No, I don't remove a discontinuity, but that's what they call it for some reason. Because I can't do that with I can't do that with a jump, right? If I have a jump, I can't draw a vertical line, it wouldn't be a function. With a vertical asymptote, I can't connect them, it wouldn't be a function. But with a hole, I could color in a little hole and it would remove the discontinuity. So they call holes removable. So if somebody asks you, where do you see a removable discontinuity? Only in A, at 2, right? Because the x minus 2 would cancel, would there be a removable discontinuity? A jump discontinuity isn't actually going to even show up on this graph.
If you fill that in.
The jump discontinuities don't occur. Like this one has an infinite discontinuity. Infinite discontinuities are vertical asymptotes. So that B has a vertical asymptote. C and D are lines and cubic functions. They're not even discontinuous. So you don't even have anything for the jump.
Yeah, it's C. It has the little bars on X.
Oh, it's greatest integer function? Okay. Yeah, the greatest integer function, if that's there, then yeah, because we know that those do this, right? They are jumping from one to the other.
Why is it called greatest integer, not least integer?
There is a least integer, isn't there?
Because what you're doing is you're taking the greatest integer that you have come to on your way to that number from left to right. So on my way to like 2.7, the greatest integer I've come to is 2.
But if it just says the bottom.
If it was negative, would it go the other way?
If it was negative on the inside, yes, it would actually be going, you'd flip it over. It would be a little thing, but you don't see a lot of that on my test. So infinite discontinuities are VAs, jumps are like step functions, or anytime you have a piecewise function, a lot of times they're jump discontinuities. All right? And we'll talk about this some other time. So keep up with your assignment sheet and enjoy your spring break.
Yes.
Anybody going anywhere interesting?
Colorado.
Skiing? Nice. Which place?
Winter Park.
Ah.
I think we might be going somewhere else as well. I don't know that.
Winter Park's huge, man. You can ski that for a week. I've
Yeah.
skied that once, and I don't know if I ever skied the same slope twice.
Oh yeah, no, it's a lot of fun.
Yeah.
That's where we usually go.
Nice. I haven't skied in a couple of years. The last day I went, my son's knee was tweaked, so we went and boarded instead. Oh, it was awesome.
Yeah.
I mean, I had never done it, and the first half of the day was miserable.
Oh yeah.
And then once I started getting the hang of it, I was like, I'm never going to ski again.
Oh yeah.
I really like it.
Yeah, it takes longer to get the hang of, but once you get the hang of it,
Is that what you do? You board a lot, or you?
I honestly
I do both. I haven't decided what I'm gonna do next week yet, but I'll probably board. Just because I haven't ever snowboarded. I've never snowboarded. I've never snowboarded out in Colorado. I've only snowboarded on the East Coast, so it was a very different experience. But people say.
Have you ever skied Colorado?
Yeah,
Okay.
but I mean, the East Coast is harder because it's more icy. So if anything, I guess it'll be easier out there.
Yeah. Like good. I mean, you never know what you'll get out there, I guess.
That's true.
Yeah, that's fine. Anybody else?
We're in New York.
Yeah.
Yeah,
Just to
so-
play, shop.
Yeah. Just, I mean, I'm turning NYU on there, so that's like
You're turning.
NYU.
Oh, okay.
You know, it's just something to do while I'm up there.
I'm going
I have
to
never been to New York.
North
Really?
Carolina.
You going to South Carolina?
North Carolina.
What to do?
My dad's family has a house there, so we're gonna stay in the mountains, and then we're in UNC.
Good.
And I just finished my home.
I've been to New York 3 times.
I've been in the airport. That's it.
I finished my
Which
second.
one?
LaGuardia, I guess.
I had JFK more.
Yeah, I don't. I was young. Like I flew in and out of there when I was kindergarten and second grade on my way to Germany. So that's it.
When I was going to Barcelona, we had like a 3-hour layover there, and I had the best Jamaican beef patties. They're so good, and that's all I think about.
You know, I had some of the best pizza I've ever had in the Houston airport. I'm trying to think of the terminal. Of what air? I mean, what air? Southwest is a
Airline.
what airline terminal it was. But man, I was with my son, or maybe I was with Carolyn, I forget. We just got a couple slices of this random pizza. I was like, oh my gosh, this is phenomenal. Maybe I was starving. I don't know. In my memory, arguably second best pizza I've ever had.
That was me with the
What about
Jamaican
the
beef
pizza on the-
patties.
Well, like in Colorado.
That's the best. Bojo's. If you're in ooh,
Where
are
is
you
it?
flying into Denver and then driving out?
Yeah.
Okay.
What's it
Now
called?
it's called Bojo's. You have to stop here.
Okay. All right.
It's pronounced BEA. Hold on, I think it. Yeah, I'll just look it up here. Bojo's. Is it BOJ? Bojo's. Okay, so Bojo's Pizza. They're all over Colorado right now. But if you're driving to the slopes, so you get off the plane, you can go in Denver and find a couple. Boulder, there's one. There's some. But you're heading on I-70 west.
Okay.
Right, so you get your rental car. Are you all doing a rental car? Or are you getting on like a shuttle? Okay. So you'll head west about 30 or 45 minutes up into the mountains. So you're heading up I-70 up. There's a little town called Idaho Springs. And it's an old mining town that's become really touristy. So it's a great little spot now. And you just pull off. There's a couple exits, pull off there and just go. You ask anybody where it is or just follow it to it. But it's an old place. That used to be a one-room place, but it's gotten so popular they keep buying the stores next to them. Now they have their own store that sells just their stuff, like shirts and stuff.
So it's like a thing.
But you buy the pizza by the pound. So you don't go in there and go, I'll take a 12-inch. You go, I want a 4-pound, a 6-pound. And you ask them, you're like, oh, I've got this many people. And you're like, how hungry are you? You probably need 4 pound. And, but it's awesome. Like maybe it's in my head because I've been going there since I was 10. We always would go there on the way to go fishing. My dad goes fishing the same place every year since he was 6 years old and he's 82. Wow. And yeah, so I go with him maybe once every 2 or 3 years.
But you were in on this before it was big.
Oh yeah. Well, it was big to locals, but it wasn't big to like random people.
Right.
And we were stuck in traffic, and my uncle was like, all right, take a left here, blah, blah, blah. And I remember he took this side route, and we ended up in Idaho Springs because he grew up in Denver. And, but anyway, yeah, it's only about 45 minutes up the hill.
All right. I'll make sure we stop there.
Yeah, so if you can coordinate it to where it's a meal time, or even if it's not. Now, it is not cheap. I once bought a pizza, couple drinks, side or whatever. It's like $100. So good. And I got a pizza way bigger than I needed because I wanted leftovers.
In New York, look at this place where I'm eating lunch. It's like 100 floors up. It's called Peak. Here, and the view's insane.
Oh, wow.
Yeah, I'm so excited.
Oh, Mr. Hurd, did I take my test? 'Cause I don't-
Yes.
I was
I
gonna-
know.
I was gonna wait till after the break.
All right, you got to be in on this. Do you remember when?
Bye, Mr. Hurry.
See it. We were handing back. Oh, you weren't here.
I was not.
No, the last test. Do you remember when I handed back test and I accidentally hit Sam?
Oh yeah.
So what I was going to do to make it up for him, but still prank him, is he made a good grade. So I was going to hand him his test, and I created a new test. This is not his, and I put the handwriting like his on there, and it's going to look terrible. And I was going to hand it to him. He's going to go. I bet he's not going to see this. He's going to go, what? And then I'm like, I'm just messing with you. So we're going to do that when we get back.
Oh,
So
that's
you have
great.
to act like you have not seen your
All
test. So I'm going to reverse it on him, and he'll have a good grade and beat us up.
Oh, that's great.
But he wasn't here yesterday when we went over or today.
Right.
That's maybe like 12 days of the making.
I know.
No.
You're probably looking at it and go, man, I was worried about this. It's like, what? How can you?
I forgot. They used the.
I said the same thing. I said f at x exists instead of x.
Dang it.
Sorry.
Y'all always the last week of the week.
I was getting his test so slow. Alright, thanks.
I
Yeah, man.
wrote my last word on my physics test when the bell rang.
Dang, does he make you get like a sense of over?
No. Well, we're actually allowed to stay a lot longer. I usually end up staying like until
the second bell rings for my essays and this essay. Was that on the last essay? I said like 8 minutes left to go.
we each started like 10 minutes late because they were filming something right at the last end.
It's not take that. What route do you do that it takes that you have to hurry out so that?
I go home and change. I live like 5 minutes.
All right. You know,
See you later. Have a good break.
yeah, you too. I ping pong.
USC this week.
Yeah, that's what you said. That's
Oh,
awesome.
I don't remember anything I told you about that.
No, you just commented that you were going to Carolina State.
Hey there.
Okay.
Are you gone?
No, I'll be back.
Oh, okay, I just don't know if you're knocking or not.
Cleaning it all up.
Hey, T. Curry,
So,
can I borrow your master key to get in my room for just a second?
Yeah.
Because I left mine at home and one of Jackson's, but actually it's Holly's son left his bag in there. We gotta get back in there. I'll bring it right back.
okay.
You got your Range Rover keys, Land Rover, whatever it is you got.
Crappy old beat up car.
It's not crappy, it's pretty nice.
Oh, it's so old, and those things are worth nothing. Like if I were to sell it, I bet I couldn't get 10 grand for it.
Oh, well, I don't know.
Piece of junk. Can't wait to get rid of it. See you. You too.